Well, what we're going to do today is we're going to talk about the data reduction procedure for climb performance. And then we're going to do climb performance this afternoon. Okay, we're going to go fly after the class, after this lecture is over. That way, you'll get that lab in. If you take a look at the calendar, we've got next Friday, we've got a holiday. We have one more meeting after that. And then we have another holiday after that. And then we're at the end of the semester, okay? So, you know, I'd like to get this slide in today so that you get at least all of these slides. So anyway, that's what we're doing today. So we'll talk about climb performance. Well, we start off, if we're going to do this, you know, on a real flight test program, and we would use the same technique that we're going to use today initially, but we do it at a series of airspeeds, okay, and altitudes. We would start at a low speed, work up, you know, and every 5 knots we would work up to our Duke double-headed climbs, okay? So we climb through the same altitude band at several climb speeds with a 5 or 10 knot spacing, probably 5 knot when we got close to the best rate of climb speed. And we conduct 2 climbs at each airspeed in opposite direction to account for the wind gradients. And we try to do them crosswind. Now you say, wait a minute, what does wind have to do with it? We're in the same atmosphere, right? Why do we have to? Anybody have any idea why we have to do opposite heading climbs? And I'll guarantee you what you'll find when you plot those climbs up is that there's a difference in the rate of climb. Why do you think that's true?
Is it a relative wind up there?
Well, you've got wind, and it is due to the wind, but you would think
your airplane moves with the air.
airplane moves with the air mass, right?
Yeah.
Well, here's what's going on. The airplane has inertia, okay? You may have heard of the downwind turn phenomena. Back in the old days, real old days, when people first started flying, it was a problem because if you made a sharp turn in those old airplanes, the airspeed would change due to the inertia of the airplane. Same thing is going on in a climb. You're climbing up, and even though you're trying to do it crosswind, you probably aren't going to get it exactly crosswind. And so what happens is, as you're climbing up, the inertia of the airplane will make the pilot think, because it'll show up in the airspeed indicator, that the airspeed is changing, so the pilot will correct for that due to the inertia of the airplane. It is not a noticeable correction, okay? But due to the fact that the airplane has inertia, and even though it's moving through the air mass, it still will have that difference, okay? Anyway, what we're going to do with this thing, and you may have seen this before, and I'll draw another chart up here on the board. What we're going to do, and this is rate of climb, and this is airspeed, is that we're going to get several different climbs to try to develop a curve that looks something like this. but but our initial plots will look something like this. We'll have time on this axis and altitude on this axis. So our original data points will start, say, here, you know, with one heading, and then we'll come back and do another climb, and every 30 seconds or so we'll take data, and then we're going to figure a line between these data points. I didn't do a very good job of it, but there we go. And then we're going to take a slope of that line, okay, at some altitude. And we're going to do a whole bunch of these curves, or we would do a whole bunch of these curves to get all of these data points. The other thing we do with this one, this point right here, where there is 0 rate of climb, is the stall speed. This point over here, 0 rate of climb, is max level flight speed. If you know those two values, then you can anchor that curve, and you only have to do it up there. What you can see from this, though, if you have to do one of these, this only gives you one of these points. What you can see from that is, it takes a hell of a long time, okay, to do climbs doing it this way, because you gotta do, you know, these are, say, every 5 knots apart. About the best rate of climbs takes a long time. That's what we're talking about here in this first thing. We are not going to do that in the class, okay? We're not going to determine the best rate of climb speed. We're going to assume that Piper already has done that, and they did, okay? So we have the best rate of climb speed that we can use. We will do 2 or 3 of these kinds of plots at different altitudes, but we'll only be looking to get the rate of climb at the best rate of climb speed. Notice here that if we do these every 5 knots, probably the best rate of climb speed is right there, right? So you wouldn't have done a climb at the best rate of climb speed. What you would do is you would do another altitude, a higher altitude, say, that would look like this. So you would end up having 2 of these kinds of curves for 2 different altitudes. So you can see that just takes forever. But from that, we can determine, you know, we plot this up and we can determine from these curves what the best rate of climb speed is, and then we can, and also what we call the best angle of climb, and from that we can plot up this being airspeed here, and this being altitude. We can plot up the best rate of climb speed and the best angle of climb speed, and they all come together in a point at what altitude? Absolute ceiling. Okay? So I'm getting ahead of myself here, ahead of the charts, but this is what we're doing. Generally, these climbs that I'm talking about over here, these climbs should be from 3 to 5 minutes. You want to make sure that you're in a stable climb, okay? So that takes quite a bit of time. And you'd repeat at several different altitudes. So, you know, I just drew 2 on the board there, but, you know, you'd probably do 3 at least. So you can see, let's see, we got every 5 knots we're doing double-headed climbs. You can see how much time this consumes. And we would, you know, we end up, these data points, we end up sort of averaging them out. Some people do that different ways. I generally just draw a single line in between 2 points and take the average, and that, you know, averages those opposite headed climbs. You know, we might plot it up this way. Here's, notice these are different climbs. This is at 70, 75, 80, 85, 90. Okay, and we started all of them at 4,000 feet. So this would only give you one of these curves. So you'd have another set of plots that would look like that to get this curve. And if you did a third one, you'd have a third set of plots like that. And then we draw a horizontal line tangent to the top of these next curves. And we end up getting, you know, a horizontal line tangent to the top of that curve gives you best rate of climb speed. And then a line from the origin, notice that this goes all the way back to 0 airspeed. Mistake most folks make when they plot this up, you know, it makes an awfully big graph. And so they'll truncate it, cut off several, and then they draw the line from the origin and you don't get the right answer. Okay, so this is the best angle of climb speed. When would you use best angle of climb?
Obstacle. Departure.
Got a tree at the end of the runway. Do you want to use best rate of climb or best angle of climb? You want to use best angle of climb, right? So that's why we get that number, you know, to be able to clear an obstacle. You're not climbing as fast as you are at best rate of climb speed, but you're not covering the distance either. So, you know, if you want to get over an obstacle, you want to use best angle of climb speed. But don't draw it from 40 knots, you get a different answer, all right? You know? And that's, like I say, the mistake I see most folks make. So we plot that all up, and we end up with the best rate of climb graph. It looks something like this. Okay, here's best rate of climb at sea level, and these plots, by the way, are from actual airplanes that I did way back when, beginning of my flight test career. I did a lot better job then, I think, than I do now. But anyway, notice that sea level best rate of climb speed for this airplane is about 82 knots, something like that. But notice that way up here, almost at it's only about 80 knots, so it only changed about 2 knots in 18,000 feet. So generally, since those curves, you know, those rate of climb curves are fairly flat on top, you can miss it by a knot or two and still be pretty close. Okay? Best angle of climb, on the other hand, starts here at about 71, and notice that, yeah, up there, it tends to increase with altitude. So it's worthwhile having this plot for the pilot, so he or she knows that, you know, if I'm going to clear that obstacle, but I'm at an airport that's 6,000 feet, I need to use a little higher speed than I would if I'm at a sea level airport. So anyway, we make those kinds of plots, and what we're going to do, let me go back to that plot. What we're going to do is use best rate speed and generate two plots like that. Okay, that's what we're going to do in the flight. So we'll be taking data, and the important data here, what's going to be changing when we're going to climb? Altitude,
Airspeed.
time, of course. Airspeed's going to be constant, okay, because of this fact, since we're going to do it best rate climb. So, you know, this is essentially constant speed. We'll be holding that airspeed. We'll be recording the altitude every 30 seconds. Okay, and this is where, you know, you have to read fairly fast. 30 seconds is actually quite a time, but you'll be surprised how fast it comes by. And we're going to record altitude versus time. And we're going to, what else is going to be changing? What's the next important parameter other than altitude?
Fuel.
Fuel is important, but not, the airplane isn't burning gas that fast. It is, you know, you're going to need to get it, but not every 15 seconds, or every 30 seconds.
The airspeed itself.
How about temperature? We're climbing, right?
Okay.
Probably the next thing that, you know, is important is temperature. All right? The third thing that's important is RPM's going to be constant, so, you know, you can say, okay, RPM's going to be so many RPM, and then you can draw a line down, okay? You don't have to write that one down anymore.
Horsepower's gonna drop because of density.
The manifold pressure is going to be decreasing as we go to altitude, right? This is a normally aspirated engine. If this were a turbocharged engine where we could hold a constant manifold pressure, yeah, we wouldn't worry about it as much, but on this one, as we go to altitude, the manifold pressure is changing. So those are the three parameters that are going to change. You can get your weight, it's important, don't get me wrong, but you can get your weight at the beginning as you start to climb and at the end. Okay, and that is just this, you know, it's just a straight line through, and it isn't going to change very much. Okay, so those are the parameters we're going to be recording. Altitude, time. So it's worthwhile to have your phone on the stopwatch mode. Usually back a few years back, before we had the, you know, everything on our phone, had to use a stopwatch. You know, as you came through the start altitude, you hacked your stopwatch. Well, same thing today. You can use your cell phone and put it on the stopwatch mode and start the stopwatch as you go through the altitude, and then record. And you're going to know what the start altitude is, so you can record that start altitude to begin with. Okay? So, anyway, we'll get altitude versus time, and you'll make that kind of a plot using the best rate of climb speed. Okay. Once you have these plots, and so you don't have a lot of work to do in this lab, I'm only going to do two altitudes. Okay, we'll start as low as we can with smooth air. Okay, so we'll have a start altitude. We'll climb up on one heading, taking data as we go, for about 3 minutes, or for 3 minutes, okay? At the end of 3 minutes, You can let whoever the pilot is know that, okay, we've got 3 minutes worth of data. Descend back down. You don't have to do anything while we're descending back down. 180-degree heading change. Do the climb again. Okay, from the same start altitude. And that'll give you, 2 data points at each 30 seconds, all right? So, and we'll do that, after we finish the second climb, we'll climb on up, pick another altitude that we're gonna start climbing at, and do that again. So that'll be the flight. And you can get your fuel quantity when you start and when you finish each altitude, and that will be sufficient because it won't change that much. Okay, then we're gonna, once we've got that data, we're gonna come back and we'll reduce that, and all you're gonna get on this, and this is the common error. I hope I do not find it like I did the 00237 error, okay? But the common error with this one is, each one of these plots only gives you one altitude. I repeat, only one altitude from each of those plots. You're gonna go in here and find where the curve is smooth, and you're gonna pick that altitude. Determine the rate of climb at that one. So it'll be the rate of climb at that altitude, okay? You don't have to reduce each one of these data points. That's the mistake everybody makes. That's my foot stomper, okay, on this, on this flight. Don't make that mistake, please. You'll have an awful lot of work to do if you do, okay? You only have to reduce on this flight, you only have to reduce 2 data points. You'll have to do 2 of these plots, but you'll only get actually 1 point off of each plot. All right, then we're going to use one of the following, yes, sir.
You just pick the smoothest line for that? Doesn't matter?
Yeah, just picking, where it's smooth, where the curve is smooth, where the data points are, generally pretty close together, not that they're spread apart this far. Pick that nice smooth place, take the slope of it, take your, if you have a triangle or a straight edge of some sort, take the slope of that line graphically, okay? Or if you hey, you guys who want to do it mathematically, go ahead, but it's so much easier to do otherwise, okay? Just take a straight edge, take the slope of that line, okay? Determine what the rate of climb is about that altitude, just. And we're going to reduce it by this method we call PIW-CIW. Hey, that's pretty close. Last time we did PIW-VIW, right? So PIW is the same. All right, you'll find that CIW is pretty close too. There are 3 methods that are used for light airplanes, and these are the 3. PIW, CIW, which I happen to like because it takes into consideration power. It only assumes that the rate of climb, the best rate of climb speed here is pretty constant. And as you saw on that graph that I showed you for a real airplane, it is, so it's the best rate of climb speed is fairly constant with altitude on a propeller-driven airplane. And it takes into account the propeller efficiency and the engine power. These other methods make some assumptions, and I personally don't like making assumptions, okay, for this kind of data. This next method, which by the way is approved by the FAA, and if you get their flight test advisory circular, you'll find that they give it in there. But it assumes that you, well, number one, that you pick a value out of the air for propeller efficiency. By the way, nobody knows what propeller efficiency really is. Okay, nobody knows. They, you know, they've got some reasonable guesses, but they really don't know. That's one. The other assumption they make is you've probably dealt with Oswald's efficiency factor in other courses. Nobody knows what the hell that is either. They always say it's about 0.8. Yeah, if you ever tried to get by flight test Oswald's efficiency factor, again, you know, you put the graph paper up on the wall over there and get your shotgun and fire at it. And then you go over and you draw a line through that. Come on, you know, I mean, those kinds of things, I don't like to make those assumptions, but this method does. So you can juggle those assumptions and kind of get the rate of climb you want. You know, not so bad. This one doesn't have power.